Did it start? Yes, it has. Is it working? It's blinking. It looks like it's working. So, we are on page stationary points, also called critical points. We're on page 6, right? Awesome. So we call any place where the derivative is equal to 0, in other words, any place where the tangent line is horizontal, completely flat, its slope is 0, we call those stationary points. They're called that because if we think about throwing a ball up in the air, it changes from going up to going down right at the top. And at that moment, for a brief, not even millisecond, it stopped. Because it was going up, had to stop, and then went down. And so at a brief moment, it was stationary or not moving. So that's maybe a little bit where that word comes from. So anytime your derivative is equal to 0, you have a horizontal tangent line, we call that a stationary point. And we call the x value that does that a critical number. We also call any point that make our original function undefined, any non-permissible values, also critical numbers. So when we were doing our number lines before, on your number lines, you are putting all the critical numbers. You're putting where your derivative is 0 plus any non-permissible values. In this equation, we had the non-permissible values. I added them as critical numbers on our number line in red. But most of them that we did just had places where the derivative was equal to 0. But -2, 0, and 2 would be the critical numbers. And they're critical because they are places where your original graph changes direction from decreasing to increasing to decreasing to increasing. So they're kind of important or critical for graphing. There are 3 types of stationary points, and we have seen all 3 of them. The first one is a maximum point. Does it make sense that when you have a maximum point, your tangent would be flat? Second one is a minimum point. Does it make sense when you have a minimum point that your tangent is flat? And the last one is called a stationary point of inflection. And you see that in your x cubed graph, where it flattens out completely in the middle, but it actually doesn't change from increasing to decreasing. We will find out later that inflection points, I guess you're going to find out right now. You're going to find out later, and also right now, that inflection points are where your graph changes from being bent downwards to bent upwards. And we're going to call this concave down to concave up. This will be sad, and this will be happy. As a result, positive happy, negative sad. So can you see that your x curve graph was bent downwards or concave down, and then after that it changes to being bent upwards. So this will be another thing that's going to help us with our graphing. But right now we're just looking at stationary points, local minimums, local maximums. Here you've got a function. Of course, at these points, your derivative would be 0. And it's at these maximums and minimum points that your function changes from increasing to decreasing to increasing. Here's our point of inflection. At a stationary point of inflection, your graph doesn't change direction. See how this one was increasing and then still increasing afterwards. If your graph changes from increasing to decreasing, you have a maximum. You see the logic in that? If you were going up and then you decide to go down, somewhere in between there where you decided to make that change, you're at the maximum height you're going to be. Same thing, if you're going down and then decide to come back up, you're going to hit a minimum at that point where you changed your mind. But at a stationary point of inflection, you just decide to stop for a second and then keep going up. And we get our first derivative test. I'm going to add a little bit to this. First of all, it says if it's a critical number, so if f prime of c equals 0, so first of all, we know that the tangent is equal to 0. And at that point, you change from positive to negative. Let's look at our little number line here. We have the point C. That was a critical point on our derivative. This is what we've been doing, drawing that derivative line. And it says it's changing from positive, so this side is positive, and this side is negative. When we draw the arrows to show increasing and decreasing, can you see why it is, like, just sort of seems common sense that point C would be a maximum? Okay, this is officially the first derivative test. The first derivative test says if you find out that at point C the derivative is 0, and if it changes from positive to negative, then point C must be a maximum. Similarly, if you see that if also f prime of C equals 0, so you would have your number line for your derivative, and this time it changes from negative to positive, meaning that it was decreasing and then increasing. I really like drawing those arrows because if you have those arrows as a decreasing function changing to an increasing function, then I think it becomes very intuitive that that has to be a minimum. But this is really important for calculus, and it will be really important for a lot of applications later on, because all sorts of businesses and the world is really concerned about maximums and minimums, right? What is the maximum amount of money we can make? That's kind of important, because if I'm running a company and I can just change a few things to make the most money possible, why wouldn't I do that? Or what's the minimum amount we need to spend to still get this done? That would be important to save money. So businesses like this from a money perspective, okay? Physics relies on it for, hey, this thing is getting shot up in the air. How high is it? What's the maximum height it's going to reach? Is this going to cause a problem or not? Okay. So, saying this again in words. A local maximum is a point where the function changes from an increasing function to a decreasing function, and the derivative is 0. So we will always need to show two things for something to be a maximum or minimum. It is not enough to show that something changes from increasing to decreasing to show a maximum. It is also not enough just to find that the derivative is 0. Because if its derivative is 0, it could be a stationary point of inflection. It could be a minimum, could be a maximum. So you always need to show two things. You want to see an example of a function that increases, then decreases, but doesn't have a maximum. Here's an example. If I just show changing from increasing to decreasing, look at this graph. I have an asymptote here. It's increasing, and then it's decreasing. But it actually doesn't exist at the asymptote. There is no maximum value. It goes up forever. So just showing that it changes from increasing to decreasing doesn't show maximum. You need two pieces of information. And that's sort of going to be a theme for figuring things out in calculus, that you need two things to show maxes or minimums. Right? Same thing. Local minimum, two things you need. You need to show decreasing to increasing, and number two, make sure that the derivative is equal to 0 at that point. So, use the first derivative test to find and classify the stationary points. We won't actually graph it completely, but the first derivative test would say, find your first derivative, negative 2x plus 5, set it equal to 0. And solve. Okay, at x equals 5 over 2, draw your number line. Plug in 5 over 2. Check if I plug in something before 5 over 2, like 0. I plug it into my derivative. You see that you get a positive value. It is increasing. If you plug in something after 5 over 2, like 10, into your derivative. So again, we write the derivative beside to remind us that we're not plugging into the original function. We plug into the derivative to find out where something is increasing and decreasing. You get a negative number, so it's decreasing. If you want to find the coordinates of your point, they're going to be 5 over 2 comma something. That's where you would have to plug it into your original equation. So you would get negative 25 over 4 plus 25 over 2. Is that right? Maybe? A little bit of mental math, hopefully. If it's not, we don't really care right now. We'll pretend my mental math worked out. Okay? So how do I find the y coordinate? I find that y coordinate by plugging 5 over 2 in for x into the original equation. The original equation gives you your points. The derivative tells you where it's increasing and decreasing. The first derivative test, this is how you would show that you fully understand the first derivative test. Since f prime of 5 over 2 equals 0, and since f of x is increasing before x equals 5 over 2 and decreasing after x equals 5 over 2. We know that that point is a maximum. So that's using calculus. You already knew that the vertex was a maximum because you've studied parabolas. You saw that this had a negative coefficient, that parabola opened down. Parabola is going to have a maximum. using the math you already knew. But now we use the first derivative test to show. And we needed to show two things, and add an e to before. First thing we need to show was that the derivative was equal to 0. The second thing we needed to show was it changed from increasing to decreasing. So every time that you want to find a maximum or minimum, you're going to need to show two things. And there are two derivative tests. This is the first derivative test. The second derivative test is called the second derivative test. There is not a third derivative test that we will be doing. Okay. Example 2. Sometimes these are a little annoying because of all the things you have to write, but here's our derivative. 4x minus 8, set it equal to 0. Solve. If you plug it in, you would get -3. And draw your number line. Plug in -2. Write your derivative. Cheat a little bit because you know, oh, no one will ever figure out that you just used the fact that you knew what a parabola did to begin with. But you showed your work. But yes, you could plug in 0 into your derivative, get -8, that part is decreasing. You could plug in 5 into your derivative, get a positive number, that section is increasing. So we can write our statement. Since, here's our first derivative test. Since f prime of 2 equals 0, and f of x is decreasing before x equals 2 and increasing after x equals 2, we know that 2, -3 is a local minimum. Now again, the word local means that some graphs have absolute minimums. A parabola is one that has an absolute minimum. It never gets lower than the vertex or never gets higher than the vertex, depending on which parabola you're looking at. But there are some graphs that have, like an x cubed graph, might have a minimum here, but it's not the absolute minimum because it goes down forever. And it has a maximum here, but it's not the absolute maximum because we see on the left it goes up forever. So we use the word local minimum and local maximum to say all we know is that everyone around the 2 is bigger. If you want close proximity, it's the smallest for everyone closely located. It might be someone far away is doing worse. With an x cubed graph, set it equal to 0, you could factor out a 3. And we get 2 critical points. So on our number line, with the derivative, you would have -1 and 3. You I would look at the factored part of your derivative, and if you plugged in something less than -1, like -5, I hope you can see that this factor would be negative. This factor would be negative. Technically, I hope you realize that 3 is a positive number, but it could come into effect if it was a -3 out in front. So I'll put a plus sign over that 3, just to remind us that that 3 is positive. And if you had plus positive number times a negative number times a negative number, I hope you can see this section is positive, and it's increasing. Plugging in 0 would still keep this one negative, but now this would be positive. That section is negative. And finally, something bigger than 3, like 7, this section now would also be positive. Positive times a positive times a positive, that would be positive. So we would have -1, comma 5. Again, I plugged the -1 into my original equation to find the y coordinate. And are you okay without writing a big long sentence? And this time we just decided to write local max. If needed to, you could write out the big sentence. And same thing, you could with 3, okay? 27 minus 27 minus 27 minus 27. Wow. Interesting mental math that happened there. That one would be a local minimum. Okay, I'd like you to try the last one on your own. I will put up the answer shortly. Here we go. How is your derivative? Did you simplify it to get 6x over x squared minus 1 squared? That's important because when you set it equal to 0, then it is easy to solve that only where the top is equal to 0, so x has to equal 0. However, this one has non-permissible values of 1 and -1 because the bottom factors. So when we draw our number line, we would include 0, -1, and 1. So the only point that is a local min is 0, 4. So check what you did, do your corrections, and then practice your quotient rule. How did you do? Notice that after you did the quotient rule, there was a common factor of x in both of the terms that you could factor out, which then simplified the bottom to just be x cubed. Then the maximum point. Set your derivative equal to 0, which means that the numerator would equal 0. And you have to solve 0 equals 1 minus 2 natural log of x. That is a log equation. How do we know something's a log equation? Is when there's an x inside of a logarithm. The strategy for solving a log equation is to get the logarithm all by itself. And then you can change it. The base is e, the exponent is a half, change it to exponential form. So you would get e to the half, and you don't have to show that it's like, if that's the only point where it's equal to 0, then that has to be the maximum. If you got more than one answer, you'd still have to do your number line to check, oh, one of them might be a maximum, one of them might be a minimum, but this one only has one value, so therefore no extra work would have to be shown. All right, try this one on your own. Okay, how did you do? I mean, if you had put, technically there should be 6 on here as well. It'd go back to increasing. And while we're doing these questions, you can think to yourself, does it make sense that the graph goes like this from what you learned in grade 12 last year? If this is a positive x cubed graph, that makes sense, it's end behavior. But now what we're finding that the x-coordinate is 2/3 there. The x-coordinate would be 6 over there. Now what this last question sort of leads us towards, and sort of a favorite style of question of an IB exam, is they like to introduce a letter into a question. So you can't just do it with your graphing calculator, you can't solve it. And often they like to start you off in the middle of your work rather than starting off at the beginning, and then you have to sort of work forwards and backwards. In order to work forwards and backwards, if you're starting in the middle of a question, you really have to know how to do a question you have to understand it very well to be able to start halfway through. Right? You ever memorize, do you still have to memorize Shakespeare? No? Oh. We had to memorize soliloquies, like to be or not to be. That is the question. I wonder how far I could get before I forgot. This is a little bit embarrassing. But I had it memorized so well that I actually could say the whole soliloquy, starting with the last word and working backwards. It really hurt my brain, but I was able to do it. It was a really good use of time, right? Like, it's really, really useful. Anyways. So, here we go. Find the derivative. Nothing hard here. We just have to work backwards. Probably first change the x to an x to the minus 1. And we get f prime of x equals 2x minus p over x squared. And now they're telling us, they jumped ahead, that there's a minimum when x equals -2. Normally we have to find the minimum values and then show that it's a minimum. Now they've already taken us to the end of this question and then say, okay, can you work backwards a little bit? What do you know? How would you figure it out? So in working backwards, what does this mean? This means when I plug in 0 for the derivative, I should have got -2 as an answer, which means I also could plug in -2 for x. When you plug in -2, the derivative has to be 0. That creates an equation that all I have to solve for is p. Since there's only one value of p, we know, well, and because they told us, that means that that's the value of p that creates a minimum. Sometimes this question could come up a little bit more difficult by just saying there's a stationary point when x equals -2. Find the value of p and classify that stationary point. Is it a maximum, or is it a minimum, or is it a stationary point of inflection? Then you would have to work further and draw your number line once you found the value of p to figure it out if it changes from increasing to decreasing or vice versa. Sometimes finding maximums or minimums with calculus is still hard because of the algebra. So there will be some questions on your exam that are like, hey, you should use a calculator. Do you know how to use your graphing calculator to find maximums and minimums? You draw your graph, go to y equals, going to draw a parabola. Maybe I won't show you. It was a dumb idea to open the calculator. Oh, maybe not. Clear. Right? 3x squared plus, I'll pick one here. Right? There we go. Not a comment. Something that when you look at, my hope is that you cannot immediately see the coordinates of the vertex of this graph. So if I hit graph, it draws it. And I can go second, above the trace button is calculate. This time I'm finding a minimum. And you can either use, here's some shortcut stuff. You can either use your arrow keys to go to the left side of, right, I'm not to the left yet, I have to arrow over more. So let's say I go far enough. There we go. I'm now to the left side, I push enter. It'll draw a little arrow. Some of the newer ones draw a dotted line. Now we need to go to the right side. And sometimes, depending, you might have to hit the arrow button a lot. A shortcut is just hitting a number. I can see that 2 is on the right-hand side. So I just push 2 and enter, and it goes to the right-hand side faster. Then it asks you to guess. I love that it asks you to guess. It's like, I think it's going to be there. Yeah. I was right. And so you get negative, or 0.833 is the x value, 9.0833 as your y value. Sometimes you can go to your regular screen and just play around with it, and it will remember the last thing you did on your graph. So you can steal values. I was going to check if it changed nicely to a fraction, but it's not happy, even though it probably is a nice fraction. Okay. So you have, I'm going to end the video here.